Stop. I don't need software update. Okay, so what we're going to look at today is vectors. Now maybe this is a new word for some people, or maybe someone has heard this before. Vectors, what are they? Has anybody heard of vector before?
Yes.
Yeah, so how would you describe to me what a vector is?
Vector.
Yeah, quantity with a direction, yeah. Now I'd like to use relative instead. Yeah, that's better. Okay, so we're going to look at vectors, and actually some people have seen vectors before. So here's first lesson is now vectors. So we have in our head already an idea of a vector. Can someone give me a simple example of a vector? Yeah, but like Tammy, give me some numbers. A very simple vector. So something like, for example, if I walk north at 1 meter per second, this is an example of a vector because it has two things.
Direction and
Yeah, a direction. Yeah, well, in this case, a speed. Yeah, but more generally, it has a direction. What's it in this case? North. And it has what else?
speed.
It has a quantity, a magnitude, a number, which is this, 1. And also a unit, although you don't have to worry too much about the unit part. So this is our simple example of a vector. So if you want the definition of a vector, so definition now. And actually, you need to know your definitions in physics because in the exam, you could get a question like define a vector or define whatever. So this is our first definition really, and it's a definition of vector. Well, actually, before I write it down, how would you define a vector? What would you say? A vector is
a quantity with direction and magnitude.
yeah, with a direction and magnitude. Yeah, very good. So a vector is a quantity with a direction and a magnitude. Or if you want something just simpler, a vector is something. Now this is first a more informal definition. Something with a size. So what I mean by that, a number, with a direction. So that's kind of informal. So if I look here, I can see this is a vector because I have a number, a size, which is this, and a direction, which is this. Okay. So a direction paired with a scalar is a vector. And if you didn't know what a scalar is, what's a scalar? I think you have that the wrong way around.
Yes.
Only magnitude, no direction. Yeah. So a scalar, maybe using our words like units and dimensions. What would you say?
You can use the number.
What I mean, like if we try to use some of our words from the first lesson, units and dimensions, what would you say?
Units or scalar.
Yeah. So a scalar. What would you say?
So dimensions are scalar. Dimensions are scalar. units are
Also scalar.
vector.
Not quite, but you have the right idea. Like dimensions are scalars, like length, mass, time. Okay, so these are examples of scalars. But my example here, 1 meter per second north. That's a vector because of the north part into it. So what could we say about a scalar? Scalar has only magnitude,
No direction.
no direction. Okay, so for example, a scalar is a real one. I'll just write one DIM for dimension for short. A scalar is a real one dimension or one dimensional object that can have a unit attached. E.g., let's say mass equals 1 kilogram. Oops, sorry, it's scrolling there. There's many different words you can use. A scalar is a one-dimensional object, a one-dimensional magnitude, or just magnitude, a real number. You know, there's many choices here. The idea is it's just one dimension. Okay. And most cases, most scalars are only positive. Give me some examples.
Weight.
Weight, yeah, weight is, yeah.
Mass.
What mass, time,
Distance.
acceleration.
Distance.
No, acceleration can be, no, not acceleration, no. Yeah. Distance is, yeah. Now, but some scalars can be positive and negative, like, for example, well, I think of more like a charge. You can have a positive charge and you can have a negative charge. But does charge have any direction? No, it's just like it's either a positive charge or a negative charge, but it has no direction. So like most cases, scalars are just positive numbers. You measure someone's height, you measure someone's mass, you measure time. So usually with a scalar, you're thinking about measuring something. The map? No, that's something different. That's a scale, not a scalar. So that's actually completely different, but similar words, yeah?
If you to classify gravity, where would you put it? In vector scale.
Gravity. Well, you mean like the force due to gravity?
Vector.
Gravity force
Is always downwards.
No, you could go up.
Well, you see, okay, it gets a bit complicated because it depends if you're talking about on the surface or in space. When you're talking about gravity, it's a vector. So we can't really say positive or negative. But when you're on Earth, gravity is always downwards. Gravity is a little bit complicated. Too complicated for this second lesson. But now gravity would be usually a vector. And velocity is a vector too. But we haven't really done those terms yet. So right now we just need to distinguish between a scalar and a vector. So I'll give you just some quick examples. So if I say Leo is 1 meter to my right, which is that? A scalar or a vector? A vector. Yeah, because what made it a vector? Because I said to my right.
Yes.
Now if I said Leo is 1 meter away,
Scalar.
now it's a scalar because you have no direction of where he is.
Yes.
So these words are the important words for this lesson, scalar and vector. Okay, so make sure you have those in your notebook, and we'll look at how to do some problems with vectors now. Just simple problems to begin with. So I need to go to a new page. Do you have this taken down?
Yes.
Okay. It's going to crash here now in a minute, I worry. Yes?
Scalar is positive always.
No. It can be negative. It's just mostly positive. Oh, here we go. Oh, good. Back to normal. Okay. So now, how do you represent a vector mathematically on paper? Well, it has two things, we said, a scalar and a direction. Okay?
Yes.
So, the direction, that's easy enough to represent. For example, if I said north, I could draw an arrow like this.
Yes.
That's clearly north, and then that would be east, and so on. But how could I represent the fact that this has a size attached to it, a number attached to it? Well, I could use the length of the arrow. So, for example, if this is 1 meter north, then this one would be 2 meters north. So, in other words, the length can be representing the scalar with the vector. So, for example, this could be vector, let's call this one vector x, and this is the symbol for vector, although it's not really used in the British books, I noticed. And this is maybe this is vector y. And you can see y is twice as long as x, because it's 2 meters north and this is 1 meter north. Okay? So, let me just make a little change to this. So, let me say this is again 1 meter north. And this one's 2 meters north. So if I add them together, what would the result be? 3 meters north. Now, if I was to change this to 1 meter north and 2 meters per second north and add them together, what do I get?
2 meters, 2 meter second meter?
Can you say that again, the last one?
Yeah, if I add this one, x plus y, 1 meter north with 2 meters per second north, can I, what do I get when I add these together?
You can't.
Well, I can't add them together.
Yeah.
So just like with vectors, the rules from the first lesson still apply. They need to be the same units or to add them together. So I can't add these vectors together. What would 2 meters per second north represent? What would something like that be?
The velocity.
Yeah, but I mean just informally, what would it be describing? Could be describing someone walking.
Yes.
2 meters, so what would it mean? Every second they move 2 meters northwards.
Yes.
Okay. Now, some things to note about vectors. This vector here is exactly the same as this vector here. Why? Well, which way do they point? North. And they're both the same length,
Yes.
roughly. So they're both the same. So you don't care where it starts, where it ends so much. You just care about the length and the direction. So this is actually very useful, because if I want to add, for example, suppose I want to add these two vectors together.
We can.
No,
add
we
them.
can.
We
We
add
can.
them.
The same.
We can. What you do is, this vector is the same as this vector. There's no difference, right?
Yeah.
They're both the same length and they're both northeast. So you can pull that vector all the way to here. So this is part of this. So what would adding them together mean? If I say 1 meter north followed by 1 meter northeast, that would be the same as going this direction.
Yes.
Now, that's easy to do roughly, but how can you do it a bit more precisely? Well, that's the first law we're going to do. So for example, let me give you our example. I have a vector here, And let's say the other vector I want to add is here. What did I do first? I moved one of the vectors, right? So I moved this one down here. And I need to put its bottom here. Yes? Now it's already on this line, so what you imagine is you slide this along. So put a dot line here. And this line needs to be the same direction as this line, yes? Now, you don't know, if you imagine this sliding down here, when this gets to here, which way will the vector point at the end? It'll point in the same direction as this one. So you draw another dotted line this way, in the same direction as this one. So the vector at the end will be here, yeah? So if I add these two together, what do I get at the end? I get this vector. Right here. So this vector, which we'll call it x, this one I'll call it y, for example, and then this is the vector x plus y. So in other words, you draw this shape and connect the corners. That's how you add the two vectors together.
You make it a different direction?
Yeah. So I'll do another example, but write this one down. So this is the law, the rule. Okay, I want to give you an example to try, so tell me when you have this taken down. It's a little loud, huh? I think I have the right cable actually. Okay, did you write this down? Yeah?
Just
Okay.
These are scalars?
No, these are vectors. All these are vectors, yeah.
What is vectors?
All vectors. That's right. You got this taken down now?
yes.
Yep. Okay. I'll give you an example to try now. So try, this is your first example to try. Just try to write this as best as you can in your notebook, okay? So try to do 3 units this way, and then 1 unit this way, and try to get this at 45 degrees, okay? Do you understand what way to draw it? So 3, maybe for example, like you could draw it 6 centimeters this way and 2 centimeters this way. Yes? Okay, can you try that? Did you draw this down?
No.
No? Can you draw this, because I need to close some programs that might be hogging my memory right now.
Do I need a ruler?
Oh, if you don't, it's okay. Just try to draw it as best as you can. Yes, but now I can't see my view full screen. Come on. Oh wait, I know. I know. Now. There we go. Got it. Okay, I need to turn a bit now. Okay, so looking at this one now. So we draw our dotted line. Well, it doesn't matter which one you start with first. So I could do this one. So that goes this way. And then I could do this one. And goes that way. So the answer you get should look something like this.
8 x y squared.
Okay. That's centimeter, of course. Okay. And it's not 8 centimeters long.
8 x y squared. What?
No, this length is not 8 centimeters. Why not? You don't just add these together.
Yeah, we measured the maybe.
You measure it, yeah. Yeah.
So 15 square. The 15 square root.
We could do that. We could use that, but
I think so.
I don't think it's this either. Because 15 square root, are you thinking Pythagoras theorem? But it's not it's not 90 here.
Oh, okay.
So I don't think we can do this. What do we do if the vector is, for example, here is vector x, and then I want vector, let's do red here, minus x. What vector do you think that would be?
The direction?
Yeah, the only thing that changes is the direction. So this is the vector here.
Yeah.
Okay. And then what about something like the vector 2x? What would that vector look like?
That's the 2 times the vector x.
Yeah, so that would look like, in my example here, maybe something like that would be 2x. It's twice the length as this,
Yeah.
but the same direction. And what about a half x?
It's the
Half the length, so that would only be something like maybe this. So that's how you take care of vectors being multiplied by a number. I've shown you how to add vectors.
You can add this together, the black one and the red one.
Yeah, what happens if you add the black and the red vector together? You get 0, yeah, they cancel. This rule has a name to it. Yeah, what is the name? Yeah, what is it?
We don't know.
Yeah. Parallelogram, sorry, oh no space. Parallelogram law.
The adding?
Yeah, this process, that's the name of it. So, all we've done now in the first class is we've have an idea of what a vector is in our head. It's something that has a direction with a scalar, with a quantity, with a single number. And how do you represent on the graph the quantity? By using the length of the vector. And how do you represent the direction?
By X and Y.
Whatever way it's pointed. Yeah. The name of this law, to add vectors together, parallelogram. Multiplying vectors are easy. If you multiply by 2, you make it 2 times bigger. A half, half the length. Negative, change the direction. What happens if you multiply a vector by 0? 0. What is this 0 vector?
No,
What does it look like?
nothing. It doesn't move.
Yeah, the problem with 0 is it has no direction really. Because which way does a point? It doesn't point anyway.
Yeah.
So it's still a vector kind of, but it has no direction. Okay. So if you want the name, what do you think would be the name of this vector? What name could you give it?
Null.
Very good. Null vector. Null vector or 0 vector, something like this.
Okay.
So null, N-U-L-L, that's when you have 0. That's an empty, so to speak. No direction. Yeah, null vector is like 0 for vectors.
It is still vector.
Still a vector.
It doesn't have a direction. So
Well, no, it has a direction, but it's not defined. So, I mean, it doesn't have a direction you can see, but it's still a vector. Now, the reason it's a vector is because you said in this example here, in maths, if you add 2 things that are the same, the result is the same type. So, for example, 1 apple, 2 apples. A number plus a number is a number. A vector plus a vector, a vector. So we're agreed that that black line is definitely a vector, yes?
Yes.
And the red one is definitely a vector, yes?
Yes.
And if I add them together, they should also be a vector.
Yes.
So the null vector, you need it to be a vector so you can still be consistent. But it's not really a vector in the sense it has no direction, okay? So it's only a vector technically. But it's not really a useful vector, yeah. So what we're really doing in the first worksheet today is just a bit of practice on parallelogram law and some of the other rules I showed you there. So you just have a worksheet here to try and add 2 vectors together. Okay. Then the next worksheet we'll do more with vectors, a little bit more difficult now. Okay. So I'll give you the first one here. Good, and exactly enough so. Yep. Yeah, I will put. These lessons are recorded, so by Friday next week you'll have your login details to log into Moodle, which is our website for notes. You can log in and you can watch the video for the lesson.
great.
Yeah, I recorded that lesson too, so you can watch the video for that lesson too.